500 million light-years away, one of the most beautiful galaxies ever photographed is bleeding. The Cartwheel Galaxy looks like a perfect cosmic ring, a glowing wheel of symmetry suspended in the constellation Sculptor. Astronomers have admired it for decades. Then James Webb pointed its infrared eye directly at it, and the elegance collapsed. Beneath the famous ring, Webb exposed a skeleton of dust, a graveyard of exploded stars, and an entire galactic body still deformed by a collision that happened hundreds of millions of years ago. What every visible light telescope showed us was a portrait. What Webb revealed was an autopsy in progress. The Cartwheel Galaxy is not a jewel. It is a wound, and it is still open. If you enjoy journeys that change how you see the universe, take a second to hit that like button and subscribe. It genuinely helps this channel keep making deep dives like this one. Now, settle in and get yourself comfortable. Let's begin. "500 million light-years from Earth, hanging in the southern constellation Sculptor, there is a galaxy that looks like nothing else in the known universe. It does not spiral gracefully like the Milky Way. It does not flatten into a featureless disk of ancient stars. It does not blur into a shapeless cloud of fading light. Instead, it forms a ring. A glowing wheel of blue and pink luminosity surrounding a bright central hub, with faint dusty streaks connecting the two like the spokes of an enormous cosmic wagon wheel. This is the Cartwheel Galaxy. And for more than 80 years, it has been one of the most visually arresting objects astronomers have ever pointed a telescope toward. The first person to notice it had no idea what he was looking at. In 1941, Swiss astronomer Fritz Zwicky was surveying galaxies in Sculptor when he found an object that defied every category he knew. It was not a spiral or an elliptical. It was round, almost perfectly round, with a bright nucleus, a luminous outer ring, and strange radial features connecting the two. Zwicky called it one of the most complicated structures awaiting explanation on the basis of stellar dynamics. No existing model predicted anything like it. The galaxy sat in the catalogues for decades as a beautiful anomaly no one could explain. Today, we know exactly what made it. And the answer is not beautiful at all. The Cartwheel Galaxy is a crime scene. Every feature that makes it visually stunning exists because of a catastrophic act of violence. Hundreds of millions of years ago, this galaxy was an ordinary spiral, probably resembling the Milky Way, with rotating arms, a central bulge, and an unremarkable structure that would have drawn no special attention. Then a smaller galaxy came screaming in from intergalactic space and punched directly through its center. Not a grazing blow, not a tidal interaction from a safe distance. A direct, nearly head-on impact through the core. The smaller galaxy plunged through the disk of the larger spiral, like a bullet through a sheet of glass. And the larger galaxy was never the same again. That collision is the single event that explains everything you see when you look at the Cartwheel today. The ring, the spokes, the intense star formation, the dusty interior, the disrupted nucleus, the active black hole at the center. Every feature of this galaxy traces back to that one moment of destruction. The Cartwheel Galaxy is not a cosmic jewel. It is the scar tissue left behind by one of the most dramatic collisions in the local universe. And what makes it even more unsettling is that the damage has not stopped. The galaxy is still deforming, still reacting, still expanding outward from the point of impact, hundreds of millions of years after the blow that broke it. To understand why this matters, you first need to understand what the Cartwheel actually is in physical terms, because the numbers alone are staggering. The Cartwheel Galaxy sits approximately 500 million light-years from Earth. That distance is so vast that the light arriving at our telescopes tonight left the galaxy before complex multicellular life even existed on our planet. We are not seeing the Cartwheel as it exists today. We are seeing it as it looked 500 million years ago, frozen in an ancient moment that we can observe but never revisit. The galaxy is enormous. Its outer ring alone spans roughly 150,000 light-years in diameter. To put that in perspective, that single ring is larger than the entire Milky Way, our galaxy, with its 400 billion stars. its spiral arms stretching across 100,000 light-years, its billions of planetary systems, could be placed inside the Cartwheel's outer ring with room to spare. The ring would swallow our entire galactic home and still have tens of thousands of light-years of space left over on either side. The Cartwheel is the dominant member of a small galaxy group consisting of 4 physically associated galaxies. 2 smaller companions are visible near it in most images. One of those companions, a bluish disrupted galaxy, is the leading candidate for the intruder that caused the collision. But even after decades of study, astronomers have not confirmed with certainty which companion was responsible. The evidence is suggestive but not conclusive. Neutral hydrogen trails detected in radio observations point toward one candidate. Disrupted morphology and signs of recent star formation point toward another. The identity of the galaxy that destroyed the Cartwheel's original spiral structure remains one of the lingering mysteries of this system. Radio telescopes have provided one of the most important clues. Neutral hydrogen, the most abundant element in the universe and the primary fuel for star formation, emits radiation at a wavelength of 21 centimeters, detectable by radio interferometers regardless of how much dust lies in the way. When astronomers mapped this emission from the Cartwheel system, they found several critical features. First, the neutral hydrogen confirmed the expansion velocity of the outer ring. Spectroscopic measurements showed that gas in the ring is moving outward at approximately 54 kilometers per second relative to the galaxy's center. This figure differs from earlier optical spectroscopy estimates, which placed the expansion velocity closer to 90 kilometers per second. The discrepancy likely reflects different measurement techniques and the regions of the ring being sampled, but both values confirm that the density wave is propagating outward at enormous speed. Combined with estimates of the ring's current radius, this velocity allows astronomers to calculate how long ago the collision occurred. Working backward from the ring's size and expansion speed, the most widely cited estimate places the collision at approximately 400 million years ago, though the exact figure carries uncertainty depending on whether the expansion velocity has remained constant over the ring's lifetime or varied as the wave encountered regions of different gas density. Second, the hydrogen maps revealed that the gas distribution within the Cartwheel is profoundly asymmetric. The outer ring contains the densest concentrations of neutral hydrogen, consistent with the density wave sweeping up gas as it expands outward, but the gas is not evenly distributed around the ring. It concentrates more heavily on one side, the side where star formation is most active, matching the asymmetry Webb later confirmed in the infrared. The inner disk between the 2 rings is relatively gas-poor, depleted by the expanding wave that swept material outward and by the infall that channeled material toward the nucleus. Third, and perhaps most intriguingly, the hydrogen observations detected a faint trail of gas extending from the Cartwheel toward one of the companion galaxies in the group. This gaseous bridge connects the Cartwheel to a smaller galaxy located to its lower left in radio images, suggesting that this companion may be the intruder that passed through the disk. The bridge would represent gas stripped from both galaxies during the transit, stretched into a filament connecting the victim to the perpetrator. This evidence is not conclusive, because tidal interactions between group members can produce similar features, but it remains the strongest physical link between the Cartwheel and a specific intruder candidate. The hydrogen data also revealed something troubling about the Cartwheel's future fuel supply. The total mass of neutral hydrogen detected in the system is lower than would be expected for a spiral galaxy of the Cartwheel's original size. A significant fraction of the galaxy's primordial gas has already been consumed by the collision-triggered starburst, converted into stars and stellar remnants that will never return their hydrogen to the interstellar medium. The galaxy is running a deficit. It entered the collision with a full tank. It is now operating on reserves that are being drawn down faster than they can be replenished. What is not a mystery is how rare this kind of galaxy is. Ring galaxies are among the most uncommon structures in the observable universe. They require a very specific set of conditions to form. A smaller galaxy must collide with a larger disk galaxy in an almost perfectly head-on trajectory, passing through or very near the center of the disk. If the angle is too steep, you get a different kind of interaction. If the impact point is too far off center, you get tidal distortion instead of a clean ring. If the smaller galaxy is too large, you get a full merger that destroys both structures entirely. Only when the geometry is almost exactly right does the collision produce the expanding density wave that creates a ring. The Cartwheel Galaxy represents one of these vanishingly rare outcomes. A galactic accident so precisely configured that it produced a structure Fritz Zwicky could not even categorize. But beyond the basic geometry of a near-center, near-perpendicular impact, the specific precision of the Cartwheel's collision explains features that remained puzzling until Webb resolved them. No real collision strikes the exact mathematical center of a target galaxy. The intruder always arrives slightly off-axis, and the degree of that offset determines how symmetric the resulting ring will be. A perfectly centered impact would produce a perfectly circular density wave expanding at equal speed in all directions. An offset impact produces a lopsided wave, stronger on the side farther from the center and weaker on the near side. The resulting ring is not a perfect circle, but a subtly distorted one, with star formation concentrated unevenly around its circumference. The Cartwheel shows exactly this kind of mild asymmetry. Its nucleus is offset from the geometric center of the outer ring, and its starburst activity is more intense on one side than the other. These features were difficult to measure precisely in optical images, but Webb confirmed them clearly in its infrared data, turning a theoretical prediction into an observed fact. The mass ratio between the intruder and the target also matters. If the intruder is too small relative to the target, the gravitational perturbation is too weak to generate a strong density wave. The ring that forms is faint, poorly defined, and dissipates quickly. If the intruder is too large, the interaction becomes a full merger rather than a transit. The smaller galaxy is captured by the larger galaxy's gravitational well, loses its orbital energy through dynamical friction, and spirals inward to combine with the target's core. No ring forms because the two galaxies become one before the density wave can propagate. Ring formation requires the intruder to be massive enough to deliver a strong gravitational kick, but small enough to pass through the disk without being captured. Estimates for the Cartwheel suggest the intruder was roughly 1/10 to 1/3 the mass of the target galaxy, placing it in the narrow range where ring formation is possible. The velocity of the encounter adds a further constraint. If the intruder crosses the disk too slowly, the gravitational interaction is prolonged and produces tidal distortions rather than a sharp density wave. The target galaxy warps and stretches, but does not form a clean expanding ring. If the crossing is too fast, the perturbation is too brief to deposit enough energy into the disk. The density wave is weak, and the resulting ring is dim. The Cartwheel's clean, prominent ring structure suggests the intruder crossed at a velocity that was neither too fast nor too slow, delivering a gravitational impulse that was both sharp enough to generate a well-defined wave and energetic enough to drive it outward, across more than 100,000 light-years of disk. These constraints, trajectory, mass ratio, velocity, and impact geometry, must all be satisfied simultaneously for a ring galaxy to form. The probability of all four conditions being met in a single galactic encounter is extremely low. Ring galaxies are estimated to constitute less than 1/10 of 1% of all known galaxies. The Cartwheel represents perhaps the most perfectly realized example of this already rare phenomenon, which is why it has served as the prototype for collisional ring galaxy studies since its identification. But the rarity of the shape should not distract from the violence of its origin, because what happened to the Cartwheel during the collision was not a gentle reshaping. It was a demolition. Before the impact, the Cartwheel was a normal spiral galaxy. It had a rotating disk of gas and stars. It had spiral arms where new stars were forming at a steady, sustainable rate. It had a central bulge containing older stellar populations. It was, by every measure, an unremarkable galaxy going about the quiet business of existing. Then the intruder arrived. When a smaller galaxy passes through the center of a larger disk galaxy at high speed, it does not simply punch a hole and leave. The gravitational disruption is far more complex and far more devastating than a simple puncture. The intruder's mass creates a sudden, intense gravitational perturbation at the center of the target disk. This perturbation sends a shockwave of compressed gas radiating outward in all directions from the point of impact. The physics is analogous to what happens when you drop a stone into a still pond. The stone strikes the surface and sends circular ripples expanding outward from the point of contact. Each ripple moves away from the center, growing wider as it travels, until it eventually dissipates at the edges of the pond. In a galaxy, the same principle operates, but at incomprehensibly larger scales and with far more destructive consequences. The expanding density wave does not merely ripple through the galaxy's gas, it compresses that gas violently as it passes. Wherever the wavefront travels, it crushes interstellar gas and dust clouds together with enough force to trigger gravitational collapse. New stars ignite along the wavefront in enormous numbers, not a gradual increase in star formation, an explosive burst. Billions of new stars created in a cosmic instant, forced into existence by a wave of compression that the galaxy never asked for and cannot control. This is the origin of the Cartwheel's famous outer ring. That luminous circle of blue and pink light is not a decorative feature. It is the current position of the expanding density wave, still ploughing outward through the galaxy's gas roughly 440 million years after the collision. Early optical measurements estimated the wave was traveling at roughly 200,000 miles per hour, though later radio observations of neutral hydrogen revised that figure downward. Either way, the wave has been racing outward since the moment of impact, and everywhere it passes, it leaves behind a trail of newly formed stars, many of them enormous, many of them doomed to burn through their fuel in just a few million years before detonating as supernovae. The outer ring is not a structure at rest. It is a detonation front still moving outward through the galaxy's remaining gas supply, and the stars it creates are not the gentle, long-lived stars that sustain stable planetary systems. Many of them are massive blue giants, blazing with luminosities thousands of times greater than our Sun. These stars live fast and die violently. The more massive a star, the faster it burns. The largest stars produced by the Cartwheel's expanding wave consume their hydrogen fuel not in billions of years, but in mere millions, lifetimes so short they barely register on the galactic clock. When they exhaust that fuel, they collapse and explode as supernovae, blasting their outer layers into space at thousands of miles per second and leaving behind either a neutron star or a black hole. The Cartwheel's outer ring is saturated with these stellar explosions. The rate of supernova detonation in the ring is far higher than in a normal galaxy. Each explosion sends shockwaves through the surrounding gas, which can compress nearby clouds and trigger even more star formation. The process feeds itself. Stars are born, they burn, they explode, and their explosions create the conditions for more stars to form. It is a self-sustaining cycle of creation and destruction, locked together in the same physical process, racing outward through the galaxy at hundreds of thousands of miles per hour. The Chandra X-ray Observatory confirmed the consequences. When astronomers pointed Chandra at the Cartwheel, they found an unusually large number of ultra-luminous X-ray sources scattered along the outer rim. These sources are the signatures of stellar corpses, black holes and neutron stars left behind by dead massive stars, now pulling material from companion stars and radiating that energy as intense X-ray emission. The Cartwheel contains more of these X-ray sources than a galaxy of its size should normally possess. The reason is straightforward. The collision triggered the formation of an abnormally large number of massive stars. Massive stars die quickly. Dead massive stars become X-ray sources. The ring is not just forming new stars. It is generating a population of stellar remnants at an accelerated rate, populating the outer edge of the galaxy with black holes and neutron stars that would not exist if the collision had never occurred. These X-ray sources deserve closer attention because they reveal something about the Cartwheel that no optical or infrared image can show directly. The objects Chandra detected along the outer ring are classified as ultra-luminous X-ray sources. This designation applies to point-like X-ray emitters, whose luminosity exceeds 10 to the 39th ergs per second, a threshold that places them far above the output of ordinary stellar mass X-ray binaries. In a typical galaxy, you might find a handful of these objects scattered across the entire disk. The Cartwheel contains an unusually large concentration of them, and nearly all of them sit along the outer ring where the collision-driven starburst is most intense. The physics behind these sources is violent and direct. When a massive star exhausts its nuclear fuel and collapses, the remnant it leaves behind depends on its original mass. Stars between roughly 8 and 25 solar masses typically produce neutron stars, objects barely 20 kilometers across but containing more mass than the Sun, compressed to densities where a teaspoon of material would weigh billions of tons. Stars above approximately 25 solar masses collapse into stellar mass black holes, objects so gravitationally extreme that not even light can escape their surface. Both types of remnant can become powerful X-ray sources if they exist in binary systems with companion stars still capable of supplying material. When gas from a companion star falls toward a neutron star or black hole, it does not plunge in directly. It spirals inward, forming a superheated accretion disk that reaches temperatures of millions of degrees. At these temperatures, the infalling material radiates intensely in X-ray wavelengths. The luminosity of the emission depends on how much material is falling in and how efficiently the accretion process converts gravitational energy into radiation. In ultraluminous X-ray sources, the accretion rates are extreme, sometimes exceeding the theoretical maximum known as the Eddington limit, the point at which radiation pressure from the infalling material should theoretically halt further accretion. The Cartwheel's outer ring produces these objects in abundance because the starburst populates the ring with exactly the kind of massive stars that become X-ray sources when they die. A normal galaxy forms massive stars at a measured rate and accumulates stellar remnants gradually over billions of years. The Cartwheel formed an enormous population of massive stars in a compressed time frame, and those stars are now dying in rapid succession, each one leaving behind a compact remnant capable of producing ultraluminous X-ray emission if it has a nearby companion to feed from. The result is a ring of stellar corpses embedded within a ring of stellar nurseries. New stars are being born along the expanding wavefront, while older stars, born just tens of millions of years earlier in the same ring, are already dead and radiating X-rays as material from their companions spirals into their gravitational wells. Birth and death are not separated by distance or time in the Cartwheel's outer ring. They coexist, physically overlapping, occurring simultaneously in the same structure. This is not normal galactic behavior. It is the signature of a system in which the natural timescales of stellar evolution have been compressed by an external event. The collision forced the galaxy to produce too many massive stars too quickly, and now it is paying the price in a currency of X-ray bright remnants that will persist in the ring for billions of years after the starburst itself has faded. This is what the Cartwheel Galaxy actually is. Not a ring of beauty, a ring of forced stellar birth and accelerated stellar death, expanding outward through a galaxy that was shattered by a collision it could not avoid. But for decades, this picture remained incomplete, because there was something hiding inside the Cartwheel that no visible light telescope could fully reveal, and it changed everything about how we understood this galaxy. The problem was dust. Dust is one of the most underestimated obstacles in observational astronomy. Interstellar dust consists of tiny grains of silicates, carbon compounds, and other materials that absorb and scatter visible light with remarkable efficiency. Even a relatively thin cloud can block starlight entirely, hiding whatever lies behind it as effectively as a wall hides what stands on the other side. The Cartwheel Galaxy is full of dust. The collision that created it did not just compress gas into new stars, it also churned up enormous quantities of dust from the galaxy's original disk, redistributed it across the interior of the ring, and generated additional dust through the supernova explosions that followed. The region between the inner ring and the outer ring, where the spokes connect the two structures, is particularly choked with dusty material. When observed in visible light, this region appears murky and indistinct. Details blur together. Structures that exist physically cannot be resolved clearly because the dust scatters and absorbs the photons before they reach the detector. The Hubble Space Telescope, one of the most powerful optical instruments ever built, observed the Cartwheel multiple times over its decades of operation. Hubble captured stunning images of the galaxy that revealed the outer ring in vivid detail, resolved individual star-forming regions as bright blue knots of light, and detected the faint spokes connecting the inner and outer rings. These images became iconic. They are the reason the Cartwheel Galaxy became famous. They are the portraits that decorated textbooks and planetarium walls and astronomy websites for years. But Hubble was working primarily in visible and near ultraviolet wavelengths, and at those wavelengths, the dust won. Hubble could see the surfaces of things. It could photograph the bright outer ring where young stars blaze in the open. It could detect the overall shape of the spokes, but it could not see through the dust to examine what lay beneath. The interior of the Cartwheel, the region closest to the disrupted nucleus, remained shrouded. The fine structure of the spokes stayed blurred. The detailed distribution of dust throughout the galaxy could not be mapped with precision, and the galaxy's active core, where a supermassive black hole sits surrounded by enormous quantities of hot gas and debris, remained partially hidden behind layers of obscuring material. This meant that every interpretation of the Cartwheel Galaxy built during the Hubble era was based on an incomplete picture. Scientists knew the galaxy was a collision product. They understood the density wave mechanism. They could see the starburst activity in the outer ring, but they were looking at the Cartwheel the way a doctor looks at a patient through clothing. They could see the shape. They could identify the obvious injuries, but they could not examine the wounds directly. They could not see what the collision had actually done to the interior of the galaxy. They could not trace the full extent of the structural damage. And so the Cartwheel remained, for decades, a galaxy understood mostly from the outside. Its surface was photographed, its ring was admired, its origin was explained. But the deeper story, the story of what the collision did to the galaxy's internal structure, what it did to the original spiral arms, what it did to the central core, how much dust was generated and where it settled, how the active galactic nucleus was being fed, that story remained locked behind a curtain of interstellar dust that visible light could not penetrate. Then, on the 2nd of August, 2022, the James Webb Space Telescope released its image of the Cartwheel Galaxy, and the curtain came down. Webb does not see in visible light. It sees in infrared, and infrared radiation passes through dust, the way radio waves pass through walls. Where Hubble saw a murky, indistinct interior shrouded in obscuring material, Webb saw directly through it. Where Hubble detected faint smudges hinting at structure between the rings, Webb resolved that structure in sharp detail. Where Hubble photographed a beautiful ring galaxy with a mysterious interior, Webb revealed the full anatomy of a galactic collision, the damage, the debris, the skeletal framework of dust and disrupted matter still holding the broken galaxy together. Webb observed the Cartwheel using two instruments simultaneously. Its near-infrared camera cut through the dust that had blocked Hubble for decades and revealed what was hiding behind it. Stars that no optical telescope had ever detected. Structures that no visible light image had ever resolved. A population of objects scattered across the galaxy that told a completely different story about what the collision had produced and where its consequences were still active. But it was Webb's mid-infrared instrument that delivered the real shock. Operating at longer infrared wavelengths, this detector did something no previous telescope could do. It did not just see through the dust, it saw the dust itself. It mapped the chemical composition and spatial distribution of dusty material throughout the entire galaxy, turning the substance that had hidden the Cartwheel's interior from Hubble into a direct source of information. And the structure it revealed beneath the galaxy's famous ring was not what anyone expected. The Cartwheel's interior was not a clean, empty space between two luminous rings. It was filled with organized structures, chemically distinct regions, and the unmistakable remnants of an architecture that predated the collision and had never been fully destroyed by it. What those structures were, what they were made of, and why their presence changes how we understand this galaxy is the core of what Webb exposed. The telescope did not simply take a higher resolution photograph. It performed a forensic examination that separated old material from new, surviving structure from collision-generated wreckage, and the galaxy's past from its present. And the galaxy that emerged from that examination was not the elegant ring the world had admired for decades. This was not a prettier picture of the same galaxy. This was a fundamentally different interpretation. A galaxy that looked ordered from a distance revealed itself, under infrared scrutiny, to be a system still carrying the physical wreckage of the event that broke it apart. Not a cosmic ornament, but a collision site. Not a structure at rest, but a structure still in motion, still evolving, still responding to an impact that reshaped every part of it from the outermost ring to the innermost core. The Cartwheel Galaxy is one of the most beautiful objects in the sky, And Webb just proved that its beauty is the visible surface of something far darker. Every feature that makes it stunning is a consequence of destruction. Every color, every glow, every luminous arc is the galaxy's ongoing response to being broken apart by a collision it could not survive intact. And the details Webb uncovered inside that broken structure are more disturbing than anyone expected. Because what the dust was hiding, and what the spokes and the core reveal about the true state of this galaxy, changes everything about how we understand it. Most people who have seen the Cartwheel Galaxy have seen it as one ring, a glowing outer circle with a bright center, connected by faint streaks. That version misses something critical. The Cartwheel does not have one ring, it has two. And the difference between them is essential to understanding why this galaxy is not just unusual in shape, but physically broken in a way that most people never realize. The outer ring is the one everyone notices. It is enormous, luminous, and unmistakable. It glows with the light of billions of young stars being born along its expanding edge. It is the structure that gives the galaxy its visual identity, the circular rim that makes it look like a wagon wheel from 500 million light-years away. But the outer ring is only the most visible consequence of the collision. It is the surface injury, the bruise you can see from across the room. The inner ring is something else entirely. It sits much closer to the galactic center, surrounding the disrupted nucleus like a tight belt of light. It is smaller, brighter per unit area, and composed of different material than the outer ring. Where the outer ring is dominated by young blue stars and active star-forming regions, the inner ring contains a denser concentration of older stars, hot dust, and the gravitational wreckage left closest to the point of original impact. The inner ring marks the boundary of the galaxy's core region, the zone where the intruder galaxy passed through and where the gravitational disruption was most intense. These two rings are not independent features that happen to exist in the same galaxy. They are both products of the same event. Both were generated by the collision. Both are expanding outward from the center, and both carry different information about what the impact did to the galaxy at different distances from the point of contact. To understand why two rings formed instead of one, you need to follow the collision forward in time from the moment of impact. When the intruder galaxy struck, it did not simply generate a single expanding wave. The gravitational perturbation at the center of the disk was complex and multi-layered. The initial impact compressed the gas nearest to the core first, generating a burst of star formation in the central region that created the dense stellar populations now visible in the inner ring. Almost simultaneously, the perturbation launched a broader, more powerful density wave outward through the disk. This second wave traveled farther, swept up more material, and grew into the massive outer ring that dominates the galaxy's appearance today. The two rings represent two phases of the same gravitational event. The inner ring is the first response, a localized compression near the point of impact. The outer ring is the sustained response, a long-range density wave that has been propagating outward ever since. They expanded at different rates and reached different distances, which is why they appear as two distinct structures rather than one blurred feature. The inner ring stalled closer to the center because the gravitational pull from the nucleus slowed its expansion. The outer ring, farther from the central mass, encountered less resistance and continued racing outward at extraordinary speed. Between these two rings lies the region that tells the most disturbing part of the story. The space between the inner and outer ring is not empty. It is filled with the wreckage of the galaxy's former structure. Dust lanes, disrupted gas, scattered stars that were flung out of their original orbits by the gravitational chaos of the collision. And the spokes, those faint radial features connecting the inner ring to the outer ring, which represent the shattered remnants of the spiral arms that existed before the impact. This intermediate region is where the collision's true destructive power becomes visible. In a healthy spiral galaxy, gas orbits in predictable patterns and star formation proceeds at a steady rate. In the Cartwheel, that organization has been destroyed. The collision scrambled the orbital dynamics of the disk. Stars that once followed circular paths now trace eccentric, chaotic trajectories. Gas was either compressed into the expanding rings or funneled inward toward the core, leaving the intermediate zone depleted and structurally disordered. What remains between the rings is not a functioning galactic disk. It is a debris field. An archaeological dig through the ruins of a spiral galaxy that no longer exists. Now consider what happened to the intruder itself. This is a detail that most descriptions of the Cartwheel overlook, but it matters enormously for understanding the full scope of the event. The smaller galaxy that caused this collision did not stop. It did not embed itself in the center of the Cartwheel and merge with the larger galaxy's core. The intruder passed completely through the disk of the target galaxy and emerged on the other side. The collision was a transit, not a capture. The intruder punched in, crossed the disk, and continued moving outward into intergalactic space. This is why the Cartwheel still has a recognizable center at all. If the intruder had remained lodged in the core, the two galaxies would have merged over time, producing a single elliptical galaxy with no ring structure. Instead, the intruder's passage was fast enough and its trajectory was direct enough that it escaped the target galaxy's gravitational well after the crossing. It deposited enormous gravitational energy during its transit, but it did not stay. It hit and ran. The speed of the transit matters. Estimates suggest the intruder crossed the disk of the larger galaxy in a remarkably short period of time, cosmologically speaking. The crossing was fast enough that the perturbation was sudden and sharp, rather than prolonged and gradual. A slower passage would have produced a different outcome. The gravitational interaction would have been drawn out over a longer period, creating tidal distortions and warping rather than a clean expanding ring. The sharpness of the density wave, the clarity of the ring structure, the fact that the two rings are distinct rather than blurred together, all of these features reflect the speed and directness of the intruder's passage. After the transit, the intruder continued moving away from the Cartwheel. It is now located somewhere in the galaxy group, possibly identifiable as one of the companion galaxies visible in images of the system. As mentioned earlier, the leading candidate is a disrupted blue galaxy that shows signs of recent star formation and structural disturbance, consistent with having recently passed through a larger system, but the identification remains uncertain. The intruder committed one of the most dramatic acts of galactic destruction in the observable universe, and then effectively disappeared into the crowd of nearby galaxies, leaving behind the evidence of its passage written across the entire structure of the Cartwheel. The consequences of that passage extend far beyond the formation of rings. The collision fundamentally altered the way the Cartwheel Galaxy forms stars, and the change is not subtle. It is extreme. In a normal spiral galaxy, star formation is a regulated process. Gas clouds collapse under their own gravity, fragment into smaller clumps, and form stars at a rate governed by the local conditions of temperature, density, and pressure. The Milky Way, for example, forms roughly 1 to 3 new solar masses worth of stars per year. This rate has remained relatively steady for billions of years. The galaxy maintains a balance between the gas consumed by star formation and the gas replenished by stellar winds, supernova ejecta, and accretion from the intergalactic medium. The process is sustainable. The galaxy can continue forming stars at this rate for billions of years into the future. The Cartwheel Galaxy does not work this way. The collision shattered the equilibrium. The expanding density wave compresses gas at rates far exceeding anything a normal spiral experiences. The star formation rate in the Cartwheel's outer ring is estimated to be many times higher than the rate in a typical spiral galaxy of comparable mass. The galaxy is burning through its gas supply at a pace that cannot be sustained indefinitely. It is not growing in a healthy way, it is erupting, producing stars in a violent, accelerated burst driven not by internal galactic processes, but by the external force of a collision that imposed an artificial compression on the galaxy's entire gas reservoir. This distinction matters because it determines what kinds of stars the Cartwheel produces and what happens to them afterward. When gas is compressed rapidly and violently, it tends to form larger clumps that collapse into more massive stars. Normal star formation produces a predictable distribution of stellar masses, with many small low-mass stars and progressively fewer high-mass stars. This distribution, called the initial mass function, has been observed consistently across many different galactic environments. But in starburst regions like the Cartwheel's outer ring, the compression conditions can skew this distribution toward higher masses. More massive stars form than would normally be expected, and massive stars, while spectacular in their luminosity, are catastrophically short-lived. A star with 10 solar masses exhausts its hydrogen fuel in roughly 20 million years. A star with 50 solar masses may last only a few million years. These are geological instants. The massive stars being born in the Cartwheel's outer ring right now will be dead before the ring has expanded appreciably farther. They will detonate as supernovae, scattering their processed material into the surrounding gas, enriching it with heavy elements forged in their cores, and leaving behind compact remnants, neutron stars and black holes, that will persist for billions of years after the stars themselves are gone. The Cartwheel Galaxy is therefore not just forming stars at an abnormal rate, it is forming an abnormal population of stars biased toward the massive end, biased toward short lifetimes, biased toward violent deaths. The outer ring is a factory for stellar extremes. It produces the brightest and most energetic stars in enormous quantities, burns through them in cosmologically negligible time spans, and replaces them with the densest and most exotic stellar remnants in the universe. The supernova rate in the outer ring reflects this process. Every explosion sends a blast wave into the surrounding interstellar medium, compressing nearby gas and potentially triggering the formation of additional massive stars. This cascade effect means that the star formation in the ring is partially self-sustaining. The supernovae that end one generation of massive stars create the conditions for the next generation to begin. The ring feeds on its own destruction, a closed loop of stellar birth and death cycling at rates far above the galactic norm. But the supernovae do more than trigger additional star formation. They generate dust, enormous quantities of it. When a massive star explodes, its outer layers are blasted into space at velocities of thousands of kilometers per second. These layers contain heavy elements, carbon, oxygen, silicon, iron, that were synthesized in the star's core through nuclear fusion during its lifetime and in the cataclysmic moments of the explosion itself. As the ejected material expands and cools, some of these heavy elements condense into solid grains, dust, tiny particles of silicates and carbon compounds, and metallic oxides that drift through interstellar space, absorbing and scattering starlight and accumulating over time into the thick clouds that obscure the interiors of galaxies. The Cartwheel's collision created an abnormally high supernova rate. That abnormally high supernova rate generated an abnormally large quantity of dust, and that dust settled into the regions between the rings, coating the spokes, filling the intermediate zone, and shrouding the galactic core in layers of obscuring material that visible light telescopes could not penetrate. This is why the Cartwheel Galaxy appeared as a mystery for so long. The collision did not just reshape the galaxy's structure, it generated the very material that hid that structure from view. The dust that blocked Hubble's gaze was itself a product of the collision. The galaxy was hiding behind its own wounds. Now consider what happened to the galactic core during all of this. Webb's instruments revealed that the galaxy's central region is not just bright, it is active. The bright core visible in NIRCam images hosts an active galactic nucleus, a supermassive black hole surrounded by enormous quantities of gas and hot dust that are being funneled inward by the collision's gravitational disruption. The core glows intensely in mid-infrared because the dust surrounding the black hole absorbs radiation from the accretion process and re-emits it as thermal emission. In a normal spiral galaxy, the central black hole may be relatively dormant. The Milky Way's own supermassive black hole accretes very little material and produces minimal radiation, effectively asleep at the galactic center. The Cartwheel's black hole is not asleep. The collision disrupted the orbital dynamics of gas throughout the galaxy, and a significant fraction of that gas was funneled inward toward the center by the gravitational chaos. Material that was once orbiting peacefully in the outer disk was knocked out of its stable orbits, lost angular momentum through collisions and interactions, and spiraled inward toward the nucleus. The result is that the central black hole has been receiving a steady supply of fuel, gas and dust channeled toward it by the very collision that reshaped the galaxy. The active galactic nucleus is surrounded by a tremendous amount of hot dust. This dust absorbs radiation from the accretion disk and re-emits it at infrared wavelengths, creating a glowing halo of thermal emission around the core. In visible light, This region appears as a bright but somewhat featureless center. In infrared, it reveals itself as a complex structure of heated material concentrated around the black hole, evidence that the core is still being actively fed by collision-driven infall. This feeding process is not instantaneous. Gas does not simply fall straight into a black hole. It spirals inward gradually, losing angular momentum through viscous interactions in the accretion disk. The timescale for material to migrate from the outer disk to the central black hole can span hundreds of millions of years. This means that the Cartwheel's active galactic nucleus is not just a current phenomenon. It is a delayed consequence of the original collision, still receiving material that was knocked out of its original orbit hundreds of millions of years ago. The galaxy's core is still digesting the collision, still processing the gravitational disruption, still channeling material inward toward the black hole through pathways that were carved open by the impact event itself. The active nucleus is not a separate feature of the Cartwheel Galaxy. It is another scar, another consequence of the same collision that created the rings and the spokes and the starburst and the dust. Now step back and look at the whole picture. The outer ring is an expanding detonation front, compressing gas and triggering explosive star formation and generating supernovae at abnormal rates. The inner ring is the compressed wreckage closest to the point of impact, containing dense concentrations of older stars and hot dust. The region between the rings is a debris field of disrupted gas, scattered stars and dusty remnants of destroyed spiral arms. The central nucleus hosts an active black hole being fed by material that the collision redirected inward. The entire galaxy is saturated with dust, generated by the same supernova explosions that the collision triggered. Every component of the Cartwheel Galaxy, every feature, every structure, every population of stars, traces back to the same event. Nothing in this galaxy operates the way it would in the absence of the collision. The star formation rate is abnormal. The stellar population is abnormal. The dust content is abnormal. The nuclear activity is abnormal. The morphology is abnormal. Everything has been reshaped, redistributed, and rewritten by the consequences of a single catastrophic impact. And there is one more detail that makes the Cartwheel's situation even more severe. A detail that has to do with what the galaxy is losing and cannot get back. The outer ring is not just moving outward through the galaxy's gas disk, it is moving outward toward the edge of the galaxy's gravitational influence. As the ring expands, it approaches the boundary where the galaxy's gas supply runs thin and eventually runs out. When the density wave reaches gas-poor regions at the extreme periphery of the disk, it will have nothing left to compress. Star formation along the ring will slow and eventually cease. The wave front will dissipate, the ring will fade, and the structure that defines the Cartwheel's appearance will begin to dissolve. But the gas consumed by the ring during its expansion is not coming back. The hydrogen and helium that were compressed into stars along the wave front have been converted into stellar material. Some of that material will be returned to the interstellar medium when those stars die, but a significant fraction will be locked permanently in stellar remnants, white dwarfs, neutron stars, and black holes that will never return their mass to the gas supply. The Cartwheel is spending its gas budget at a rate that cannot be sustained, consuming its raw material for star formation in a single accelerated burst, rather than rationing it across billions of years the way a normal spiral does. This is the equivalent of a biological organism running a catastrophic fever. The elevated activity is not a sign of health. It is a sign of crisis. The galaxy is burning through its reserves in response to an injury, and when those reserves are exhausted, the galaxy will enter a period of decline. Star formation will drop, the outer ring will lose its luminosity. The brilliant blue knots of newborn stellar clusters will dim and redden as the most massive stars die and are not replaced. The Cartwheel will become quieter, dimmer, and structurally simpler over the coming hundreds of millions of years. What the Cartwheel looks like today, the luminous ring, the blue star clusters, the radiant outer edge, is a temporary state, a fever state. The galaxy is not thriving, it is reacting, and the reaction is consuming it. This is what older telescopes showed us in pieces. Hubble captured the surface, Chandra mapped the X-ray remnants, Spitzer detected the infrared glow of heated dust. Each telescope contributed a fragment of the picture. But none of them could see the whole thing at once. None of them could penetrate the dust deeply enough to trace the full anatomy of the collision damage from the outermost ring all the way down to the feeding black hole at the center. That changed when Webb arrived. And what Webb saw in the infrared, the dusty skeleton, the resolved spokes, the detailed structure of the core, turned the cartwheel from a beautiful image into a forensic document. A detailed record of what a galactic collision does to every part of a galaxy, from its outermost gas to its innermost black hole. The Cartwheel is not a ring galaxy that happens to have an interesting history. It is a collision aftermath masquerading as a galaxy. Every photon it emits is shaped by the violence that created it, and the features that Webb exposed beneath the dust, the features that Hubble could never fully resolve, reveal just how deep and how persistent that violence truly is. The forensic detail tells the rest of the story. What Webb's instruments actually found when they looked through the dust and mapped the Cartwheel's hidden interior is a galaxy that is far more damaged, far more complex, and far more unstable than its elegant ring suggests. Every telescope that observed the Cartwheel Galaxy before Webb was looking at the surface of the problem. Hubble saw the skin. Chandra saw the heat signatures of the dead. Spitzer caught the thermal glow of warm dust. Each instrument captured a fragment, but none could see the full internal structure at once. None had the combination of infrared sensitivity and angular resolution needed to cut through the dust and resolve what lay beneath it. When Webb turned toward the Cartwheel in its early months of operation, it carried two instruments that together would dismantle the galaxy's visual illusion and replace it with something far more revealing. The first instrument was Webb's near-infrared camera, known as NIRCam, operating at wavelengths between 0.6 and 5 microns. At these wavelengths, dust becomes partially transparent, allowing the camera to detect objects that visible light telescopes cannot see. The second instrument was Webb's mid-infrared instrument, known as MIRI, operating between 5 and 28 microns. At these longer wavelengths, dust does not just become transparent, it becomes visible. Dust grains that absorb starlight are heated by that absorption and re-emit the energy as thermal radiation in the mid-infrared. MIRI does not look through dust the way NIRCam does. It looks at dust directly. It maps the distribution, composition, and temperature of dusty material throughout the galaxy, turning the very substance that blocked Hubble's view into a source of information rather than an obstacle. Together, these two instruments gave Webb something no previous telescope possessed: the ability to simultaneously see through the Cartwheel's dust and see the dust itself. NIRCam revealed the stars and star-forming regions hidden behind the obscuring material. MIRI revealed the material itself, its chemical composition, its spatial distribution, its relationship to the structures that the collision created. The combined image was not merely a higher-resolution photograph of the same galaxy Hubble had already captured. It was a fundamentally different kind of observation. The difference between photographing the outside of a building and performing a structural inspection of its foundations. The NIRCam image arrived first in public understanding, and its immediate impact was the revelation of stars. Thousands of previously hidden stars and compact star-forming regions appeared across the galaxy as individual blue dots. These were young stellar objects, many of them still partially embedded in the gas clouds from which they were born, invisible to Hubble because the surrounding dust absorbed their optical light before it could escape. In near-infrared, that light passed through the dust and reached Webb's detector, revealing a galaxy far more populated with young stars than optical images had suggested. The distribution of these young stars told an important story. They were not concentrated exclusively in the outer ring, as Hubble's images had implied. They appeared across the entire galaxy, scattered throughout the intermediate region between the two rings and clustered along the spokes. This meant that star formation driven by the collision was not confined to the expanding density wave at the outer edge. It was occurring throughout the disrupted interior of the galaxy, in regions where the collision had compressed gas along the remnant spiral structures. The Cartwheel was forming stars in places that had been invisible to previous observations, and that changed the accounting of the galaxy's collision response significantly. NIRCam also revealed a critical contrast between two populations of stars. In the galaxy's central core, the camera detected a smooth, even distribution of light. This smoothness indicated a population of older stars, stars that predated the collision, stars from the galaxy's original spiral structure that had survived the impact and settled into stable orbits near the nucleus. Their smooth distribution told astronomers that the inner core, while disrupted, had not been completely demolished. Some of the original galaxy's architecture persisted at the center, buried beneath layers of hot dust and new material but structurally intact. Outside the core, the distribution changed dramatically. The light became clumpy, irregular, and patchy. These clumps corresponded to young star clusters, groups of newly formed stars still embedded in the gas and dust from which they had recently condensed. The contrast between the smooth older core and the clumpy younger exterior was stark. It mapped the collision's reach in visual terms. The center retained a memory of what the galaxy used to be. The exterior was dominated entirely by what the collision had forced it to become. This distinction between old and new, between surviving structure and collision-generated chaos, had been theorized before Webb's observation, but no telescope had been able to image it so cleanly. Webb drew a visible line between the galaxy's past and its present, showing that both coexist within the same system, layered on top of each other like sedimentary rock, recording different geological eras. The Cartwheel is not a galaxy that was destroyed and rebuilt. It is a galaxy where the original structure and the collision aftermath occupy the same physical space, interpenetrating and overlapping in ways that only infrared imaging can separate. To appreciate the magnitude of what Webb accomplished, it helps to walk through the history of how the Cartwheel looked under each previous generation of telescopes, because the progression reveals how profoundly the interpretation of this galaxy changed with each improvement in capability. The first detailed image came from the Hubble Space Telescope in 1995. At that time, Hubble captured the Cartwheel in visible light and produced an image that became iconic. The outer ring appeared as a vivid blue circle, studded with bright knots that Hubble resolved as gigantic clusters of newborn stars. Immense loops and bubbles blown into space by supernovae were visible along the rim, described at the time as going off like a string of firecrackers. The faint spokes between the rings were barely detectable, appearing as ghostly wisps that could easily be mistaken for imaging artifacts. The inner ring was visible but featureless. The core appeared as a smooth, bright concentration of light, with no resolved internal structure. The intermediate zone between the rings was murky and indistinct, filled with a haze of dust that Hubble could not penetrate. That image established the Cartwheel's public identity. It was beautiful. It was the aftermath of a collision. But the details of the collision's internal consequences were hidden. Hubble could see the surface, but not the tissue beneath it. In 2018, Hubble revisited the Cartwheel with improved processing. The reprocessed image was sharper, and the spokes became slightly more visible. But the fundamental limitations remained. The dust was still opaque, the core was still featureless, the intermediate zone was still a murky unknown, a better photograph of the same incomplete picture. Then Webb arrived, and the comparison between the Hubble view and the Webb view is not a matter of slightly better resolution or marginally deeper exposure. It is a categorical shift in what is visible. In Hubble's image, the spokes are thin, pale, barely distinguishable from the background. In Webb's image, the spokes are among the most prominent features in the galaxy, glowing intensely in mid-infrared with silicate and hydrocarbon dust emission. In Hubble's image, the region between the rings appears as an indistinct fog. In Webb's image, that region is resolved into detailed structures, showing clumps of young stars, threads of dust, and the skeletal architecture of the disrupted spiral arms. In Hubble's image, the core is a smooth, bright spot. In Webb's image, the core reveals the hot dust concentration surrounding the active galactic nucleus, differentiated from the surrounding older stellar population by its distinct infrared signature. The transition from Hubble to Webb is the transition from viewing a galaxy in visible light, where dust hides the interior and only the most luminous surface features are detectable, to viewing it in infrared, where the dust itself becomes a source of information and the hidden interior is laid open. Every feature that was ambiguous in Hubble's data became concrete in Webb's. Every structure that was hinted at became confirmed. Every question that the optical view left unanswered, the infrared view resolved. But the true revelation of Webb's observation came from Miri, and what Miri found was the galaxy's skeleton. In the composite image released by NASA and ESA, MIRI data appears as red colouring overlaid on the NIRCam data rendered in blue, orange and yellow. The red structures that MIRI detected represent regions of the galaxy rich in specific chemical compounds. Hydrocarbon molecules, including polycyclic aromatic hydrocarbons, complex organic molecules that glow brightly when energized by nearby starlight. Silicate dust, composed of silicon and oxygen, bonded into mineral grains similar to much of the dust found on Earth, and other chemical compounds associated with processed interstellar material, elements that were forged in the cores of stars, expelled by supernova explosions, and condensed into solid grains that now permeate the galaxy's interior. These dusty, chemically rich regions did not appear randomly. They formed a pattern, a series of spiraling structures stretched between the inner ring and the outer ring, connecting the two like the supports of a bridge. These structures were the spokes. And under Webb's infrared instruments, they were transformed from the faint, barely visible wisps that Hubble had detected into prominent, detailed, structurally complex features that dominated the galaxy's mid-infrared appearance. The spokes glowed red with silicate dust. They curved in spiraling arcs that bore an unmistakable resemblance to spiral arms. And that resemblance was not coincidental. The spokes are spiral arms. Or rather, they are what remains of spiral arms after a head-on collision has passed through the galaxy that contained them. Before the collision, the Cartwheel Galaxy was a spiral. It had rotating arms of gas and stars extending outward from a central bulge, just like the Milky Way or Andromeda. When the intruder galaxy passed through the center of that spiral, it did not erase those arms instantly. The gravitational disruption was catastrophic, but it was not total. The arms were broken, distorted, and stripped of much of their gas as the expanding density waves swept material outward into the rings. But the underlying gravitational structure of the arms, the orbital pathways along which stars and gas had been traveling for billions of years, did not vanish overnight. What happened instead was a process of deformation. The expanding rings disrupted the spiral pattern, stretching and warping the arms into the radial features that now connect the inner ring to the outer ring. The spokes are the remnants of those arms, pulled and twisted by the competing gravitational forces of the expanding wave and the residual rotation of the disk. They are not new structures created by the collision. They are old structures that the collision broke but did not fully destroy. Webb proved this by showing that the spokes contain material that predates the collision. The silicate dust and hydrocarbon compounds MIRI detected in the spokes are consistent with the chemical composition of a mature galactic disk, material that was present in the original spiral before the intruder arrived. Some of the dust in the spokes is newly generated by supernova explosions occurring within them, but a significant portion represents pre-existing interstellar material that was gathered up and concentrated along these structures by the gravitational wake of the collision. This is a critical detail. It means the Cartwheel Galaxy has not moved on from the collision. It has not reformed into a new, stable structure. It is still carrying the wreckage of its former self within its current architecture. The spokes are fossils embedded in a living galaxy, remnants of a previous identity that the collision interrupted but did not erase. The galaxy we see today is a hybrid. Part collision product, part surviving spiral. Neither fully one thing nor the other. And the spokes are the physical evidence of that unresolved duality. The chemical detail MIRI provided went even further. The instrument distinguished between different types of dust in different parts of the galaxy. In the outer ring, where young massive stars energize their surroundings with intense ultraviolet radiation, the dominant infrared emission came from hydrocarbon-rich dust glowing orange as it absorbed and re-emitted stellar energy. This dust is associated with active star-forming regions. It traces the locations where new stars are currently being born, heated by the very stars it helped create. In the spokes, the dust composition shifted. The dominant material became silicate dust, heavier mineral grains that glow at slightly different mid-infrared wavelengths than hydrocarbon molecules. Silicate dust is characteristic of more processed interstellar material, the kind of dust found in mature galactic environments, rather than in the immediate vicinity of newborn stars. The presence of silicate-dominated dust in the spokes reinforced the interpretation that these structures contain older material from the pre-collision galaxy, redistributed but not replaced by the collision's aftermath. Webb essentially performed a chemical autopsy of the Cartwheel Galaxy. It did not just photograph the galaxy in better resolution, it identified what the galaxy is made of, where those materials are located, and how their distribution maps onto the collision history. The outer ring is made of collision-driven starburst material. The spokes are made of pre-collision galactic disk material. The core is made of ancient stellar populations buried under collision-redirected dust. Each chemical signature corresponds to a different chapter of the galaxy's history, and Miri read them all simultaneously. This is what separates Webb's observation from everything that came before. Hubble took a portrait. Webb took an X-ray of a broken bone. The portrait shows you the surface. The X-ray shows you the fracture. And in the Cartwheel's case, the fracture runs through the entire galaxy. Now consider the core. Webb's instruments provided the first clear infrared view of the active core that earlier data had only hinted at. Previous X-ray and radio observations detected signs of nuclear activity, but the thick dust surrounding the center obscured the accretion environment from optical telescopes. Webb's infrared sensitivity penetrated that dust and revealed the thermal structure of the core directly. The mid-infrared emission showed a concentrated knot of heated material wrapped tightly around the nucleus, glowing at wavelengths consistent with dust grains, absorbing high-energy radiation from the accretion process and re-emitting it as thermal infrared. The quantity of dust surrounding the nucleus is itself a significant finding. The core is not lightly veiled, it is buried. A thick, obscuring concentration of heated material wraps around the central black hole, dense enough to block optical observations entirely, and massive enough to sustain bright mid-infrared emission across the entire central region. This thick shroud of heated material is not a pre-existing feature of the galaxy. It is a direct consequence of the collision's ability to channel material inward from the disrupted disk, concentrating gas and dust around the nucleus at rates far exceeding what an undisturbed spiral would deliver to its center. The active galactic nucleus adds another dimension to the Cartwheel's collision story. The collision did not just trigger star formation in the outer disk. It activated the central black hole by providing it with fuel. Material that was orbiting peacefully in the spiral disk before the collision was knocked out of its stable orbits, lost angular momentum through gravitational interactions, and began spiraling inward toward the nucleus. This infall process has been ongoing for hundreds of millions of years, feeding the black hole a steady supply of gas and dust that sustains its active state. In a normal spiral galaxy, the central black hole might accrete very little material. It sits at the gravitational center, but without a delivery mechanism to funnel gas inward, it remains largely dormant. The Milky Way's own supermassive black hole is in this state right now. It has a mass of roughly 4 million suns but accretes so little material that it produces almost no detectable radiation. It is, for all practical purposes, asleep. The Cartwheel's black hole is not asleep. It was woken up by the collision, and the material that woke it up is still arriving, still falling inward, still feeding the accretion disk that powers the active nucleus. The collision did not just wound the outer galaxy. It reached all the way into the core and turned on the engine at the center. The damage extends from the outermost expanding ring to the innermost feeding black hole, a continuous chain of consequences, linking the surface to the center through hundreds of thousands of light-years of disrupted galactic structure. Webb's composite image captures all of this in a single frame. The blue dots of NeoCam show individual young stars and star-forming regions scattered across the galaxy, many of them visible for the first time. The orange and yellow tones show older stellar populations and intermediate structures. The red glow of Miri traces the dust, the hydrocarbons, the silicates, the heated material surrounding the active nucleus. Together, these layers reveal the Cartwheel not as the clean, symmetrical ring that optical images suggested, but as a multi-layered wreck of old and new material, surviving and collision-borne structures, all tangled together in a system that has not yet figured out what it is becoming. The chemical specificity of Miri's detection deserves more attention because it demonstrates the precision of the forensic work Webb performed on this galaxy. Different chemical compounds emit and absorb infrared radiation at characteristic wavelengths. Polycyclic aromatic hydrocarbons, Complex molecules consisting of carbon and hydrogen atoms arranged in ring structures produce strong emission features at wavelengths near 3.3, 6.2, 7.7, 8.6, and 11.3 microns. These molecules are ubiquitous in star-forming regions throughout the universe. They are energized by ultraviolet radiation from nearby young stars and re-emit that energy in the mid-infrared, producing some of the brightest emission features in the infrared spectra of galaxies. In the Cartwheel, MIRI detected these hydrocarbon features most prominently in the outer ring and in specific regions along the spokes where young stars are present to energize the surrounding material. Silicate dust produces a different set of spectral features. Silicon-oxygen bonds in mineral grains create broad absorption and emission features, centered near 9.7 and 18 microns. These features are characteristic of processed interstellar dust, the kind of material found in mature galactic disks, where generations of stellar nucleosynthesis have enriched the medium with heavy elements. MIRI detected silicate features most prominently in the spokes, in the intermediate zone between the rings, and in the dusty cocoon surrounding the active galactic nucleus. The spatial separation of these two chemical signatures, hydrocarbons concentrated where young stars are forming and silicates concentrated in the remnant spiral structures, allowed Webb to effectively color-code the Cartwheel by collision history. Regions dominated by hydrocarbon emission are regions where the collision triggered new activity. Regions dominated by silicate emission are regions where pre-existing material from the original spiral has been redistributed but not fundamentally altered. The chemistry maps onto the dynamics. The galaxy's past and present are written in different molecular signatures, legible to any instrument sensitive enough to read them. This level of chemical discrimination was impossible for any telescope before Webb. Hubble operated primarily in optical wavelengths where dust is an obstruction rather than a source of information. Spitzer, NASA's earlier infrared space telescope, operated in similar wavelength ranges to MIRI but with far lower spatial resolution. Spitzer could detect the total infrared emission from the Cartwheel, but it could not resolve the chemical differences between the spokes and the outer ring or map the dust distribution with the precision needed to separate collision-borne material from pre-existing galactic material. Webb's combination of infrared sensitivity, angular resolution, and spectral coverage allowed it to perform a chemical analysis of the galaxy's interior that no previous instrument could attempt. This is where Webb's observation becomes genuinely disturbing. Not because it found something alien or unexpected, but because it found exactly what a collision should produce, and showed that the Cartwheel has not even begun to recover from it. In theoretical models of ring galaxy formation, the collision is followed by a long period of dynamical evolution during which the galaxy gradually reorganizes itself. The expanding density wave eventually dissipates as it reaches the edge of the gas disk. The disrupted spiral arms attempt to reform through the normal process of differential rotation. The starburst activity fades as the compressed gas is consumed. The active nucleus quiets down as the supply of infalling material runs out. Over hundreds of millions to billions of years, the galaxy is expected to settle into a new equilibrium, possibly resembling a spiral again, possibly becoming something else entirely. The Cartwheel has not reached that equilibrium. It is not even close. The outer ring is still expanding. The spokes are still present and prominent. The starburst activity is still raging. The nucleus is still active. The dust is still everywhere. Every indicator that astronomers use to assess whether a collision aftermath has stabilized tells the same story. This galaxy is still in the acute phase of its response to the collision. The collision occurred approximately 400 million years ago. That is a long time by human standards, but a relatively short time by galactic standards. Galaxies evolve over timescales of billions of years. 400 million years is enough time for the density wave to travel a significant distance outward through the disk, and enough time for multiple generations of massive stars to be born and die in the outer ring, but it is not enough time for the galaxy to process the full consequences of the impact and settle into a new stable configuration. The Cartwheel is caught in the middle of a transformation. It is no longer the spiral it used to be. It is not yet whatever it will eventually become. It exists in a state of structural ambiguity, carrying the remnants of its former identity in the spokes, while simultaneously building a new identity through the rings and the starburst activity and the active nucleus. It is a galaxy between forms, a system that has been knocked off its evolutionary trajectory and has not yet found a new one. Webb's image captures this transitory state with a precision that no previous telescope achieved. The older stars in the core, the disrupted spokes, the expanding rings, the scattered young star clusters, the heated dust, the active nucleus, they are all visible simultaneously in the composite image, layers of different epochs and different processes coexisting within the same frame. The image does not show a galaxy at rest. It shows a galaxy in motion, still responding, still changing, still carrying the energy of the collision outward through its structure at hundreds of thousands of miles per hour. And there is something else that Webb's observation highlighted. Something that most descriptions of the Cartwheel overlook because it does not fit the narrative of a beautiful ring galaxy. The Cartwheel is not symmetrical. In popular images, the galaxy appears as a near-perfect circle. This impression is partly an artifact of viewing angle and partly a consequence of how images are processed for public release. When astronomers examine the Cartwheel in detail, particularly in Webb's infrared data, the asymmetries become obvious. The outer ring is not uniformly bright. Star formation is more intense on one side than the other, with the most active starburst regions concentrated in specific sections of the ring rather than distributed evenly around its circumference. The inner ring is not perfectly centered within the outer ring. The nucleus is offset from the geometric center, a direct consequence of the fact that the intruder galaxy did not strike the exact center of the original spiral, but impacted slightly off-axis. These asymmetries are not cosmetic, they are dynamical. The off-center impact created an asymmetric density wave that compressed gas more strongly in some directions than others. The side of the ring farthest from the nucleus received the strongest compression and shows the highest rates of star formation. The side nearest to the nucleus received weaker compression and shows lower activity. This asymmetry is consistent with numerical simulations of off-center ring galaxy collisions, which predict exactly this kind of lopsided star formation distribution. Webb resolved these asymmetries clearly. The MIRI data showed that dust concentration varies significantly around the ring, with thicker accumulations in the most active star-forming sectors. The NIRCam data revealed that the density of young stellar clusters is not uniform around the ring but peaks in specific regions. The galaxy is not a perfect wheel. It is a warped, off-center, lopsided collision product whose apparent symmetry dissolves under close inspection. Webb's field of view also captured two smaller companion galaxies alongside the Cartwheel, and what the telescope revealed about these companions adds another layer to the story of the collision's broader consequences. The most prominent companion is a spiral galaxy, visible to the upper left of the Cartwheel in the composite image. Under Webb's infrared instruments, this companion displayed striking features of its own. MIRI detected significant hydrocarbon dust emission throughout the spiral, glowing in the same red hues that characterize the Cartwheel's spokes and outer ring. The companion also showed signs of active star formation, with NIRCam resolving young stellar clusters distributed across its disk. The question this raises is whether the companion's activity is related to the Cartwheel's collision. Galaxies in compact groups interact gravitationally even without direct collisions. Tidal forces from a nearby massive galaxy can compress gas in a smaller neighbor, triggering enhanced star formation. The Cartwheel is the dominant member of its group. Its mass influences the orbits and internal dynamics of every other galaxy in the system. The companion's dusty, star-forming appearance could be a coincidence, the natural state of a gas-rich spiral going about its business independently. Or it could be a secondary consequence of the same event that reshaped the Cartwheel, gravitational tides from the collision disturbing the companion's gas distribution and triggering its own modest starburst. Webb's data alone cannot resolve this question definitively. But the companion's presence in the same infrared frame as the Cartwheel serves as a reminder that galactic collisions do not occur in isolation. The Cartwheel exists within a group. The intruder that caused the collision came from this group. The companions that remain are still gravitationally bound to the Cartwheel and will continue interacting with it over billions of years. The collision was not a one-time event involving two galaxies. It was an event that occurred within a gravitationally connected system, and its consequences ripple outward through the group dynamics in ways that are still unfolding. The second companion, smaller and less prominent, appears near the Cartwheel in the image but has received less scientific attention. Its properties are less well characterized, but its presence underscores the compact nature of the Cartwheel's galaxy group. 4 galaxies occupying a relatively small volume of space creates a dynamically active environment where future interactions are not just possible but likely. This matters because it reinforces the central point. The Cartwheel Galaxy is not an elegant cosmic ornament. It is the messy, asymmetric, structurally compromised aftermath of a violent event. Its apparent beauty is a product of distance and limited resolution. The closer you look, the more damaged it appears. The higher the resolution, the more the symmetry breaks down. Webb looked closer and at higher resolution than any previous telescope, and what it found was a galaxy far rougher, far more disordered, and far less finished than its public image suggests. The difference between the Hubble view and the Webb view of the Cartwheel Galaxy is not merely a difference in image quality. It is a difference in interpretation. Hubble showed a ring galaxy, Webb showed a collision aftermath. Hubble showed a shape, Webb showed a process. Hubble showed what the galaxy looks like, Webb showed what the galaxy is. And what the galaxy is, when stripped of optical illusion and examined through the penetrating clarity of infrared, is a system that has been fundamentally broken by a collision and is still living with the consequences, still forming stars at unsustainable rates, still feeding its central black hole with collision-driven fuel, still carrying the shattered remnants of its original spiral arms through its interior, still expanding its outer ring into the surrounding void. The galaxy's future state cannot be predicted from current data. Simulations can model what should happen next. The ring should slow, the spokes should dissolve or reform into new spiral arms, the starburst should fade, but the Cartwheel exists in a regime of dynamical complexity where predictions carry significant uncertainty. 2 competing forces are at work: the residual rotation of the original disk, which wants to restore spiral structure, and the expanding density wave, which is still actively reshaping the galaxy's gas distribution. Which force wins, and when, and what the resulting galaxy looks like, depends on variables that are not yet fully constrained. What Webb showed is that this competition is still unresolved. The galaxy has not picked a direction. It is still caught between what it was and what it might become, suspended in a transitory state that could last for hundreds of millions of years more. And every detail Webb revealed, every hidden star, every dusty spoke, every asymmetric clump of star formation adds to the picture of a galaxy that is not recovering gracefully, but struggling through the longest and most consequential aftermath of its existence. The Cartwheel Galaxy is one of the most photographed objects in extragalactic astronomy. It has been observed by nearly every major space telescope of the past 3 decades. But Webb did something none of those telescopes could do. It peeled back the dust, separated the old from the new, mapped the chemistry of the wreckage, and showed the galaxy as it truly is rather than as it appears in visible light. And the galaxy it showed is not the one most people think they know. It is darker, it is messier, it is more violent, and it is far from finished, because the Cartwheel's current state is not a stage in recovery. It is a portrait of a galaxy that may never fully return to what it was before the collision that defined it. NASA described the Cartwheel Galaxy in a single sentence that should have alarmed everyone who read it. The agency said that Webb's observations underscore that the Cartwheel is in a very transitory stage. That sentence appeared in the official release accompanying the image. It was surrounded by descriptions of star formation and infrared instruments and the beauty of the composite photograph. Most people skimmed past it. But that sentence contains the most important truth about the Cartwheel Galaxy, and it is the truth that transforms this galaxy from a spectacular image into something genuinely unsettling. The Cartwheel Galaxy is not a stable object. It is not a finished structure. It is not a galaxy that experienced a collision in its past and has since settled into a new equilibrium. It is a galaxy that is still in the process of being reshaped by a collision that happened hundreds of millions of years ago and whose consequences have not yet played out. The transitory stage NASA described is not a brief intermission between 2 stable states. It is an extended, unresolved, dynamically chaotic period during which the galaxy does not know what it is becoming, and that period is far from over. To understand what this means, Consider what normally happens to a galaxy over the course of its lifetime. Most galaxies evolve slowly. The Milky Way has existed for approximately 13 billion years. Over that span, it has consumed smaller satellites, built up its disk through steady accretion, and maintained a broadly stable spiral structure. Changes occur, but across timescales so long that the galaxy's identity remains consistent from one epoch to the next. A snapshot taken 5 billion years ago or 5 billion years from now would show a recognizable spiral. The galaxy evolves within a continuous identity. It remains itself. The Cartwheel Galaxy lost that continuity. The collision did not merely alter the galaxy's properties, it interrupted its evolutionary trajectory entirely. Before the impact, the Cartwheel was a spiral galaxy following the same kind of slow, stable evolutionary path that the Milky Way follows today. After the impact, that path was erased. The spiral structure was demolished. The gas distribution was scrambled. The star formation rate was driven to extreme levels. The central black hole was activated. The entire dynamical state of the galaxy was reset by a single catastrophic event, and the galaxy has been living in the aftermath ever since. Living in the aftermath is not the same as recovering from it. Recovery implies a trajectory toward a known destination, a return to a previous state, or an arrival at a new stable one. The Cartwheel is not on a clear trajectory toward either. It is caught between two competing forces that are pulling it in different directions, and the outcome of that competition remains genuinely unknown. The first force is residual rotation. Despite the collision, the Cartwheel's disk has not stopped spinning. The stars and gas that survived the impact still carry the angular momentum they possessed before the intruder arrived. This residual rotation acts as a restoring force, attempting to reorganize the disrupted material back into a spiral pattern. The spokes that Webb revealed so clearly in infrared are evidence of this process. They are the remnants of the original spiral arms, distorted and broken but still present, still tracing curved paths through the galaxy's interior that echo the spiral structure that existed before the collision. The galaxy is trying to rebuild its arms. The rotational dynamics that create spiral patterns in normal disk galaxies are still operating, still shaping the distribution of gas and stars, still pushing the system toward a spiral configuration. The second force is the expanding density wave. The collision-generated shockwave that created the outer ring is still active, still propagating outward, still compressing gas and triggering star formation along its front. This wave is a disruptive force. It redistributes gas from the inner disk to the outer edge, depletes the reservoir of material available for normal star formation, and imposes a radial structure on the galaxy that competes directly with the rotational structure the disk is trying to restore. As long as the wave continues expanding, it works against the reformation of spiral arms by pulling material outward and preventing it from settling into stable circular orbits. These two forces are not compatible. One wants to restore the galaxy to a spiral, the other wants to continue reshaping it as a ring. The galaxy cannot satisfy both simultaneously, and the resolution of this conflict depends on which force dominates, which in turn depends on how much gas remains in the disk, how far the density wave travels before it dissipates, and how quickly the residual rotation can reassert itself over the disrupted material. Simulations of ring galaxy evolution offer possible outcomes, but they do not converge on a single prediction. Some models suggest that the density wave will eventually exhaust the available gas and dissipate, allowing the residual rotation to gradually reform spiral arms over the following billion years. In this scenario, the Cartwheel would slowly transition back toward a spiral morphology, though the resulting spiral would be different from the original. It would be gas-poor, having consumed much of its fuel in the starburst. It would contain an older stellar population in its core and a younger, collision-born population in its outer regions. It would carry the chemical signatures of its collision history in the distribution of heavy elements throughout its disk. It would be a spiral, but a scarred one, marked permanently by the event that broke it. Other models suggest a different outcome. If the collision was energetic enough and the gas depletion severe enough, the galaxy may not reform as a spiral at all. Instead, it might settle into a lenticular configuration, a disk galaxy with a smooth stellar distribution, but no active spiral arms and very little ongoing star formation. Lenticular galaxies are common in the universe. They represent a transitional type between spirals and ellipticals, containing a disk structure but lacking the gas supply needed to maintain spiral features. The Cartwheel could become one of these, a galaxy that remembers its disk origin in its shape, but has lost the raw material needed to sustain the spiral identity it once had. A third possibility exists, more speculative but not ruled out by current data. If the Cartwheel's galaxy group is dynamically active, another collision could occur before the galaxy has time to stabilize. Ring galaxy groups are compact by nature. The companion galaxies orbit relatively near the Cartwheel, and gravitational interactions among group members can produce additional encounters over timescales of hundreds of millions to billions of years. A second collision, even a less direct one, could further disrupt the galaxy's structure and delay, or permanently prevent the reformation of stable spiral arms. The Cartwheel could be destined not for recovery, but for repeated disruption, each encounter stripping away more gas, triggering more starbursts, and pushing the galaxy further from its original identity. The Cartwheel is the most famous ring galaxy in astronomy, but it is not the only one, and comparing it to other collisional ring systems reveals both how representative and how extreme it is within its class. ARP 147 is one of the most visually striking comparisons. Located approximately 430 million light-years from Earth, this system consists of a blue ring galaxy and the elliptical galaxy that collided with it, roughly 150 to 200 million years ago. Hubble captured ARP 147 in remarkable detail, showing a ring of intense star formation with bright blue knots distributed around its circumference. Chandra detected X-ray sources along the ring, similar to the ultra-luminous X-ray sources found in the Cartwheel, confirming that the same cycle of collision-triggered massive star formation, followed by rapid stellar death and remnant production, operates in other ring galaxies as well. But ARP 147's ring is smaller and less developed than the Cartwheel's, representing an earlier or less energetic stage of the ring formation process. The Lindsay-Shapley ring offers another comparison. This ring galaxy lies approximately 300 million light-years away and displays a nearly perfect circular ring of star formation surrounding a displaced nucleus. Like the Cartwheel, its ring was generated by a smaller galaxy passing through the disk of a larger spiral. Unlike the Cartwheel, its spokes are far less prominent and its inner ring is less well defined. The Lindsay-Shapley ring appears to represent a ring galaxy at a different dynamical stage, one where the expanding wave has swept most of the disk material into the outer ring, leaving the interior relatively clean compared to the Cartwheel's dust-choked, spoke-threaded interior. These comparisons matter because they show that the Cartwheel is not an isolated curiosity. It belongs to a recognized class of collision products, each at a different point in the ring galaxy life cycle. Some are younger, with rings still close to the nucleus. Some are older, with rings that have expanded to enormous diameters and begun to fade. The Cartwheel sits at a stage where the ring is fully developed, the spokes are still prominent, and the starburst is still vigorous. It is, in many respects, the most photogenic stage of ring galaxy evolution, the moment when the most features are simultaneously visible, and the collision damage is most completely on display. But the comparison also underscores how temporary this stage is. Ring galaxies at later evolutionary stages show faded rings, diminished star formation, and dissolved spokes. The Cartwheel will eventually look like them. The spectacular features that define it today are features of a specific moment in the collision timeline, not permanent properties of the galaxy. Astronomers studying the Cartwheel are not studying a stable object. They are studying a snapshot of a process, caught at the instant when the evidence is most vivid. None of these outcomes is certain. All of them depend on parameters that are not yet fully measured. The Cartwheel's gas mass, the velocity profile of its residual rotation, the current energy of the expanding density wave, the orbital dynamics of the companion galaxies, all of these quantities carry significant uncertainties that prevent astronomers from making a definitive prediction about the galaxy's long-term future. What can be said with confidence is that the Cartwheel is not in a state where its future is obvious. It is in a state where multiple futures remain possible, and the galaxy itself has not yet committed to any of them. This uncertainty is not a failure of scientific understanding. It is a genuine property of the system. The Cartwheel Galaxy exists in a regime of dynamical complexity, where small differences in initial conditions can lead to very different long-term outcomes. The same collision that created the beautiful ring also created a system so far from equilibrium that its evolutionary path cannot be predicted, with the precision astronomers are accustomed to applying to more stable galaxies. The Cartwheel is, in a very real sense, a galaxy whose future is still being written by forces set in motion hundreds of millions of years ago. And while that future remains unwritten, the present tells a story that deserves to be heard clearly, because it is a story that challenges how we think about beauty in the cosmos. The Cartwheel Galaxy is beautiful. That fact is not in dispute. Every astronomer who has observed it, every image that has been published, every documentary that has featured it, has acknowledged its visual impact. The ring shape, the luminous outer edge, the blue knots of star formation, the faint spokes connecting the center to the rim, these features combine to produce a galaxy that looks designed. It looks intentional. It looks like something that was meant to be this shape, as if the universe carved it deliberately into a cosmic wheel for reasons of aesthetic pleasure. That impression is an illusion, and Webb dismantled it. What makes the Cartwheel beautiful is the same thing that makes it broken. The luminous outer ring glows because billions of stars are being born in an unsustainable collision-driven burst. The blue knots are detonation sites where massive stars ignite and explode as supernovae, seeding the ring with the very dust that obscures the galaxy's interior. The spokes are shattered remnants of spiral arms broken by the gravitational shock of the collision. The bright core is an active galactic nucleus, a supermassive black hole fed by gas. The collision redirected inward. Every feature that contributes to the Cartwheel's beauty is a product of violence. Every photon that makes it glow is emitted by a process that traces back to the collision. The galaxy does not look beautiful despite the collision. It looks beautiful because of it. The violence created the structure. The destruction generated the light. The injury produced the symmetry. Remove the collision, and the Cartwheel would be an ordinary spiral galaxy indistinguishable from billions of others. It is the act of breaking that made it extraordinary. This creates an uncomfortable relationship between beauty and damage that extends far beyond a single galaxy. The universe is full of objects that are beautiful for reasons that, examined closely, turn out to be violent. Nebulae that glow in vivid colours are the expanding debris fields of dead stars. Spiral arms that sweep gracefully across galactic disks are density waves compressing gas with enough force to trigger gravitational collapse. The auroras that light up polar skies on Earth are the visible consequence of charged particles from solar eruptions colliding with atmospheric molecules. Even the night sky itself, the canvas on which all astronomical beauty is displayed, is dark only because the universe is expanding fast enough to redshift the light from distant sources beyond human perception. Beauty in the cosmos is almost never gentle. It is almost always the visible surface of a physical process that, if you were close enough to experience it directly, would annihilate you. The Cartwheel Galaxy is simply one of the clearest and most dramatic examples of this principle. It takes the relationship between beauty and destruction and writes it across 150,000 light-years of galactic structure in a form so visually arresting that people admire it without ever asking what it cost. Webb asked what it cost, and the answer is everything the galaxy used to be. The Cartwheel Galaxy that existed before the collision is gone. It was an ordinary spiral. It had a quiet nucleus. It had rotating arms. It had a steady, sustainable rate of star formation. It had a future that would have looked much like its past, billions of years of gradual evolution within a stable identity. That galaxy was destroyed in a single event that lasted a cosmically insignificant amount of time. The intruder crossed the disk and was gone, but the spiral it left behind was already dead. Its arms were broken, its gas was displaced, its nucleus was activated. Its entire dynamical state was overwritten by the energy of the collision. What exists now is not the same galaxy. It carries some of the same material. It occupies the same region of space. It retains fragments of the original structure in its spokes and its older stellar core, but it is not the galaxy it was. It is something new, something that was forced into existence by an external event, something that did not choose its shape or its properties or its future. The Cartwheel Galaxy is not an evolution, it is an imposition, and what Webb revealed, more clearly than any previous telescope, is that the imposition is not over. The galaxy is still being shaped by the collision. That timescale is long enough for the density wave to cross most of the disk, long enough for dozens of generations of massive stars to be born and die in the outer ring. But it is not long enough for a galaxy to process the full consequences of a collision this severe and settle into a new equilibrium. The aftermath is not winding down. It is still in progress, still living through the consequences, still carrying the energy of the impact outward through its structure at tens of thousands of miles per hour, hundreds of millions of years after the blow that started it. 400 million years have passed since the collision, and the Cartwheel is still a collision aftermath. Not a post-collision galaxy, not a recovered galaxy, an aftermath, a system still in the process of absorbing a blow it received when fish were the most sophisticated vertebrates on Earth, and the first primitive forests were only beginning to take root on land. This is what dark reality means in the context of this galaxy. It does not mean horror, it does not mean fear, it does not mean some fabricated sensational discovery that changes physics. It means that the real nature of the Cartwheel Galaxy, when examined with instruments capable of seeing through its dust and separating its chemical layers and resolving its structural details, is fundamentally harsher than its appearance suggests. The galaxy is not a ring of light. It is a ring of consequences. It is not a cosmic ornament. It is a wound measured in light years, still open, still active, still changing. Webb did not discover something new about the Cartwheel Galaxy. Webb discovered what was always there but could not be seen. The dust hid the spokes. The optical illusions smoothed the asymmetries. The distance softened the violence into beauty. Webb removed those filters and showed the galaxy as it actually is. A massive, disrupted, dust-choked, starburst-saturated, nuclear-active collision scar wrapped in a ring of forced stellar birth that is consuming the galaxy's gas supply at a rate that guarantees the current structure cannot last. The Cartwheel will change. It must. The gas will be exhausted. The ring will fade. The starburst will end. The nucleus will quiet down as its fuel supply is consumed. The spokes will either dissolve into the disk or reform into new spiral arms, depending on which of the competing dynamical forces prevails. Hundreds of millions of years from now, the Cartwheel will look different, perhaps calmer, perhaps more ordinary, perhaps unrecognizable compared to the galaxy Webb captured in 2022. There is one more reason the Cartwheel's story resonates beyond its own 500 million light-year distance. It is a preview of what awaits our own galaxy. The Milky Way and Andromeda are on a confirmed collision course. Andromeda is approaching at approximately 250,000 miles per hour and will arrive in roughly 4 to 5 billion years. The collision is inevitable. The encounter will not produce a ring galaxy. The mass ratio is close to 1:1, and the approach angle is wrong for a transit. Instead, the two spirals will merge over several billion years into a single massive elliptical galaxy. Astronomers have already named Milky Way. But even though the outcome will differ from the Cartwheel's ring, the underlying physics will be the same. The same tidal forces that shattered the Cartwheel's spiral arms will distort the Milky Way's disk. The same density wave mechanisms that triggered the Cartwheel's starburst will compress gas clouds in both galaxies and ignite bursts of star formation far exceeding current rates. The same gravitational disruption that funneled material toward the Cartwheel's central black hole will drive gas toward the supermassive black holes at the centers of both the Milky Way and Andromeda, potentially activating one or both as luminous galactic nuclei. The same process that generated an overabundance of massive stars and ultra-luminous X-ray sources in the Cartwheel's outer ring will produce populations of short-lived giants and their compact remnants throughout the merged system. The Cartwheel Galaxy shows what galactic collisions do. It displays the consequences in real time, written across 150,000 light-years of disrupted structure. The Milky Way will not form a ring, but it will experience the same categories of damage: disrupted orbits, forced star formation, gas depletion, nuclear activation, structural destruction. The Cartwheel is not just a distant curiosity, It is a laboratory demonstrating the physics that will eventually reshape our own cosmic home. Our sun will likely survive the merger. The vast distances between individual stars make direct stellar collisions extraordinarily unlikely, even during a galactic impact. But the night sky will transform beyond recognition. The familiar constellations will dissolve as stars are flung into new orbits. The galactic disk will warp and eventually disappear as the spiral structure is destroyed. The Milky Way as we know it will cease to exist, replaced by something new, something shaped by the same violent forces that turned an ordinary spiral in the constellation Sculptor into the Cartwheel Galaxy. Webb showed us what collision damage looks like when examined with the sharpest infrared instruments ever built. Billions of years from now, if any observers remain in the merged remnant of the Milky Way and Andromeda, they will live inside that kind of damage. The Cartwheel is not just a story about a distant galaxy, it is a story about what collisions do to galaxies. And our galaxy has an appointment with one. But right now, in this moment, frozen in the infrared light that travelled 500 million years to reach Webb's detectors, the Cartwheel Galaxy exists in the most revealing state it will ever occupy. It is close enough to the collision that the damage is still fresh, far enough from it that the consequences have had time to propagate throughout the entire structure. It is a galaxy caught at the precise moment when the full scope of what was done to it becomes visible. If you have an instrument capable of seeing it, Webb is that instrument. And the galaxy it revealed is not the one we thought we knew. The Cartwheel Galaxy is one of the most elegant objects in the observable universe. It is also one of the most honest portraits of what a galactic collision leaves behind. Those two facts are not separate. They are the same fact, seen from two different distances. From 500 million light-years away, through a visible light telescope, the Cartwheel is a jewel. From the same distance, through Webb's infrared detectors, the Cartwheel is a ruin. Both views are real, but only one of them tells you what the galaxy actually is. The real shock of Webb's observation is not that the Cartwheel Galaxy looked different in infrared. Every galaxy looks different in infrared. The real shock is that better vision did not make the Cartwheel more beautiful. It made it more damaged, more complex, more violent, more unstable, more temporary, more clearly the product of an event that broke a galaxy apart and left it to rebuild itself from the wreckage, with no guarantee that the rebuilding will succeed. That is the dark reality of the Cartwheel Galaxy, not a secret hidden in the data, not a conspiracy of light and shadow, just the straightforward, physically verified truth that one of the most visually stunning galaxies in the sky is also one of the clearest portraits of what ongoing post-collision damage looks like when you have an instrument precise enough to see it. The Cartwheel Galaxy is not a mystery, it is a diagnosis. A galaxy, examined under the sharpest infrared eye ever built, found to be carrying the structural, chemical, and dynamical consequences of a collision that shattered its identity and replaced it with something that glows brilliantly from a distance and reveals its fractures only under close inspection. 500 million light-years away, in the constellation Sculptor, a galaxy that used to be a spiral is still trying to decide what it will become. Its outer ring is still expanding. Its spokes are still glowing with the dust of a destroyed past. Its black hole is still feeding. Its stars are still exploding. And its beauty, the beauty that made it famous, is still the visible surface of a violence that has not ended and may not end for hundreds of millions of years to come. Webb saw all of this, and now so do you. The Cartwheel Galaxy is not what it appeared to be. It never was. It was always a collision scar dressed in starlight. Webb simply had the eyes to prove it.